Okay, so this is a crash course on ordinary least squares regression. This is sort of the standard regression that gets taught in introductory research methods courses. And if you have a pretty good handle on OLS regression, and what we'll try to do today is sort of talk through how it's used, and then you should be able to understand and interpret results in a report or in an academic paper that are using this kind of regression or other kinds of regression that all operate in sort of a similar kind of way. And so that's the goal today, is to get us to a point where we can interpret and understand what's happening in these models. So let's begin with what regression is. Regression is a way of describing a relationship between two variables, right? And so here I have a scatter plot of high school GPA and my outcome, or my independent x-axis sort of side of things, and then on the y-axis I have university GPA, and you might make a causal argument that if you did better in high school, maybe you'll do better in college. And in fact, if we kind of look at the points and where things land, it kind of looks like that's the case, that things kind of trend upward, there's a positive relationship. And we could maybe use correlation to describe that. And if you've looked at correlation before, you know it runs from -1, a perfect negative relationship, to +1, a perfect positive relationship. And the closer it is to those extremes, the stronger the relationship is. And so maybe you could look at that and say, oh, maybe that's a 0.5 correlation. It's positive and it's fairly strong. Regression gives us a slightly different way of describing that positive relationship. It describes it as the equation for a line. And so that red line that sort of traces through the center of those data points, that's your regression line. And it follows the same format for a line that you probably learned in high school algebra: y equals mx plus b, or y plus a plus bx. Well, in statistics, we use a slightly different sort of notation, but the same basic structure. Y equals b sub 0 plus b sub 1 times x sub 1. So the b sub 0 is our y-intercept. It's where our line crosses the y-axis. So in this one, it looks like a little bit under 2.5. And then the b sub 1 is a slope. It's a slope value associated with x sub 1. And so every time we increase our x value by a unit of 1, what effect does that have on y? And so if we were to go from 2 GPA to 3 GPA, how would that change our university GPA, our outcome, our predicted GPA? And so we can think about that relationship in terms of a line. Well, we can take that idea of describing the relationship between two variables using the equation of a line, and we can extend it to tell more complex stories. Lots of things that we're interested in the social world are really complicated. There's lots of factors that contribute to outcomes. And so we can build in multiple different factors into our explanation, into our prediction of our dependent variable, our y variable. And because it allows for us to tell these more complicated, sophisticated stories, regression ends up being one of the most widely used statistical tools across the social sciences, across the policy community, and even across the business community. And so it really is useful to be able to understand regression and interpret the results of a regression analysis, to be able to process and understand empirical research. And so if we're looking at a multiple regression equation, so we're using multiple independent variables to explain our dependent variable, we're just modifying that equation of a line slightly. So we still have an outcome y, we still have a y-intercept b sub 0, we still have a slope b sub 1, and we're multiplying that times one independent variable, x sub 1. But we might do that again. We might have a second slope for a different variable, a different relationship between that x sub 2 and our y, or outcome variable. And so we have a second slope. And in fact, we could do multiple different independent variables, each with their own slope, each with their own relationship, that would help us collectively to tell a more complex and interesting story about what's going on with y. Okay, so why is that really important? Why do we want to tell those more complicated stories? Well, it helps us to build better predictions and see things more clearly. And so if I were to point you to the sort of scatter plot on the left here with the black dots, you might look at the regression line, that blue line that kind of slants down, sort of a negative relationship cutting through the middle of those points. And you might look at that and say, that doesn't seem like it's doing a very good job. Those points are all over the place. Some are like way up at the top, some are way down at the bottom. It's really messy. It doesn't seem like our line's doing a very good job. And that's a fair critique. That relationship between x and y doesn't seem to, it seems to be a lot messier than just what the line might suggest. In the second scatter plot, we've sort of separated out those same points into two different groups. And so we've built into our analysis whether those points are part of group A, the sort of pink or salmon colored points, or whether they're part of group B, the sort of bluish tealish points. And we've developed a separate line for each of those. And we can see that those lines do a somewhat better job explaining the results. Also, interestingly, the direction of those lines has changed, right? And so this is something called Simpsons paradox, that a pattern that we see in general might not actually hold for subgroups. And so one of the things that multiple regression allows us to do is it allows for us to do statistical control and start breaking out different groups and different patterns and seeing how these relationships hold up and change as we tell a more complicated story, where what's happening with group A and group B looks very different than the overall big picture that you would see if you weren't able to take into consideration some of those different subgroup patterns. Okay, so regression helps us to see lots of different things. It can also help us move in the direction of establishing causality. And so one of the things that we've talked about in my research methods class is a variety of different ways to try to nail down causality, right? So it could be experimental designs, it could be comparative case study designs. And there's a couple sticky problems that come with trying to nail down causality, right? So you have to figure out time order. There has to be a pattern of some kind, but a pattern's not enough, right? That simply because you see a correlation doesn't really guarantee that that's a causal relationship. That correlation could be driven by some other factor, right? And so one of the sort of famous examples of this is that drowning and ice cream sales seem to be related, which might suggest that ice cream is causing drowning or drowning is causing ice cream sales. But it turns out that there's a third factor that's driving both of those, and that is hot weather, right? That when it's really warm out, people go swimming and therefore drownings go up. And when it's really hot, people go and they buy ice cream. And so ice cream sales go up. And so even though we can see a correlation or a pattern, there might be something else that's driving it. And if we're going to nail down causality and make it an argument that two things are linked in a causal way, we need to rule out all those alternative explanations. And multiple regression gives us a way of doing that we can build in those other factors into our analysis, like temperature, that can help us to rule out those as potential explanations. And if a relationship that we're interested in continues to hold up when we've added in various different possible explanations that might explain or account for the pattern we're interested in, and that relationship still holds, that moves us in the direction of being able to say these things seem to be related in a way that's not just spurious, that's not just something else pushing them in the same direction. They seem to be connected in a way that we can't really explain other than maybe they're causally related. And so multiple regression and this idea of statistical control and telling more complex stories is a very common tool used by social scientists to try to advance arguments about causality. Regression also gets used for forecasting, and it gets used in the business community or the policy community, because once we have an equation for a line, we can use that information to project out what's likely to happen in the future. And again, in my research methods class, we look at Abramowitz's time for change model, in which he forecasts presidential vote share for the incumbent party, and is able to do that with just a couple of variables. He looks at unemployment rate, he looks at presidential approval, he looks at whether there's an incumbent running, and based on just a couple of factors, he can make a forecast about how a party is going to do in the presidential election by simply plugging in values for those different independent variables. One of the nice things about Abramowitz's model is that it's really pretty simple, right? That it's a very parsimonious, it's elegant in that we're working with just maybe 3 or 4 different independent variables. And with that, we can do a really good job of explaining our outcome, right? So it's not just parsimonious, it's also powerful. It helps us to predict and forecast in a way that's accurate, to explain a great deal of the variation. In fact, Abramowitz's forecast, just using these 3 or 4 different variables, ends up getting within about 2%, 1 to 2.5% of the popular vote consistently over the course of the last 70, 80 years. That's pretty good when you consider that he's just plugging in 3 or 4 numbers in June of an election year and is able to get forecasts that are about as accurate or more accurate than public opinion surveys of thousands of people. And so given that he's able to take just a handful of factors and make forecasts that seem to be pretty accurate, that tends to suggest that he's got a good model for forecasting. Okay, so let's talk a little bit about how to evaluate that. And to do that, we're going to look at some of the regression output that you get from SPSS. SPSS, if you haven't worked with it before, is a fairly straightforward statistical program that most folks start learning statistics on. It's fairly straightforward in terms of the interface. That having been said, the output that you get for regression looks pretty much identical to the output you would get if you did this analysis in Stata or SAS or R, or even if you did your statistical analysis in Excel. It's going to kick out results that look pretty much like this. So one of the first things that we would want to look at if we were sort of looking at the results of a regression model, and in this case we have a model that's looking at the predicted grade that people will get in a research methods graduate class. That's our dependent variable. And in our model, we have two independent variables that we're using to predict grades. We're looking at your overall GPA, and we're looking at GRE quantitative scores. And so those are our two variables. And so the first thing you want to do is you want to figure out what's your dependent variable, what are your independent variables that we're using to predict or forecast our dependent variable. And so once we've sort of identified those things, then we ask ourselves, is this model doing a good job? Are we able to use those handful of things to actually explain fairly effectively what's happening? And that's our R-square value. And so if you follow that sort of arrow a little bit around and over, it'll point you to that first box up there where it says R-square. And there's a number in that box. And that number is the percent of the variation in our dependent variable that we are able to explain with our model. So if you think about grades as some people are doing really well and some people are not doing really well, and there's sort of this variation across individuals in terms of how they're performing in a class, we're able to explain 51.3, so 0.513, 51.3% of that variation of who's doing well and who's not doing well with our model with just these two independent variables. So a terrible model would be explaining 0. A perfect model would be explaining 1 or 100%. But with these two variables, we were able to explain more than half. And so maybe I might make a case that that's parsimonious. I might make a case that that's even a fairly powerful model. Maybe I can make it better by adding in study time, or whether you're part of a study group or something like that. But for the time being, we can sort of look at that and say, wow, that's getting at how good of a job this model is doing, the R-square. The other thing we might want to do is we might want to build the equation of a line so that we could do a forecast, right? So if I know this is the general pattern for past classes, I might sort of figure out, okay, so what's my current GPA? What was my GRE quantitative score? And I could use that information to make a prediction about how I would do in that class. But if I wanted to do that, I would need to be able to sketch out the equation of a line. And so I would need to find where those values are, the intercept and those slopes. And if we follow the line around here again, it points us to that third box and to that sort of second column in that third box that has the letter B at the top of it. You might recall that when we talked about the mathematical notation in regression, it's y equals b sub 0 plus b sub 1, x sub 1, that kind of a thing. Well, this first column is where those b's are coming from. These are the values that we're going to be using to build our regression equation. So the regression equation is y, our outcome, predicted grade, equals our y-intercept. In this case, there's no row that says y-intercept. Instead, there's one that says constant. For whatever reason, statisticians have decided that instead of saying y-intercept, they're going to say constant. It might be related to calculus, where sort of things in an equation that don't have a variable attached to them are called constants. I guess the y-intercept would be a constant in that case because there's not a variable that's attached to it. There's not an x that goes with it. So that constant row and that B column, that 63.8, that is our y-intercept that we'll plug into our equation. Okay, so then I go to the next row, and I've got my variable GRE Q, or for the quantitative score, and there's the slope that's associated with that 0.019. Okay, so that's my slope, and that's the slope for my X variable for the GRE quantitative. And so I would plug that piece into my model. I do plus 0.019 times the X value for my GRE quantitative. And so if I had, a GRE quantitative score of 100, I would multiply 0.19 times 100, and I'd get 1.9, I guess, would be the increase it would have on my grade. If I had a perfect GRE score of 800 on my quantitative section, so 800 times 0.19 would be a little under 16 points. I might expect my grade to go up by 16 points if I had a perfect GRE score. So maybe that's interesting. I can move down to that third row, the GPA, and I'll find the slope for that. And so the slope in this case is 5.041. And so I'll plug that into my equation, because that's also part of the story we're telling, that your current GPA is a part of the forecast and part of the prediction for how you're going to do in this class. And so I guess if we thought about it as I failed every class I ever took and my GPA is 0, then if I plugged a 0 in for that X value, 0 times 5 is 0, I wouldn't expect to get any boost from my GPA in terms of predicting, what's going to happen in that class. If my GPA was perfect, I'd aced every class I ever took and I had a 4.0, I would plug a 4 in for that X value, and I guess 4 times 5 is 20-ish. And so that would suggest to me that if I have a 4 there for that X value, for that GPA value, I should expect my grade to be 20 points higher than it would be otherwise. So again, with those 3 different numbers, I can build an equation of a line, and then I can plug in my GPA, I could plug in my GRE quantitative score, and I could work that equation out and get a prediction for how I should do, assuming the relationship holds, in this class on quantitative research methods. Okay, so at this point, you should be able to look at statistical output and say, okay, there's that R square that I want to pay attention to. I can maybe find some slopes and the y-intercept, and I can use that to build the equation of a line. But before we get too carried away with that, I think we need to circle back and talk a little bit about sampling theory, because these statistics, the R square and the betas, the y-intercept and the slopes, all of those are statistics, and we should be interpreting statistics with a little bit of a grain of salt. And that means going back and talking briefly about sampling theory and how samples behave and how samples operate. So statisticians have studied random sampling pretty thoroughly, and they have a pretty good idea about some of the properties of samples. And so one of the things that they know is that samples are on average correct. Right? If you were to go and take every potential sample that could ever be taken from a population and analyze them, on average, those samples would give you the right answer. But not every sample is going to give you the right answer. Sometimes your samples are going to be too high. Sometimes your samples are going to be too low. Samples tend to bounce around. So we know that there's variation in terms of samples. We also know a little bit about what that variation looks like. We know that if you were to take every single possible sample from a population, and in fact, statisticians do this, it's called doing a Monte Carlo test, where you pull samples from a data set and generate every possible sample you could possibly pull. And you analyze each of those samples and plot the results. Those results follow sort of a bell-shaped distribution, a normal distribution. And so most of the bouncing around ends up being pretty close to the true population value, the center of the bell curve. Occasionally you get results that are a little bit further out into the tails of that bell curve, and that can happen with random variation, but most of the time results are closer into the center. And we also know that as our sample sizes get bigger, that bell curve kind of compresses in around the true population value. So larger samples are less likely to be off by a lot than smaller samples. And so we know some things about samples and how they behave, and we can use that to maybe ask some skeptical questions about whether or not the results we see in this regression model are actually real, or whether they're maybe just samples bouncing around and random sampling variation. And so the way that we do this is we sort of imagine this thing called the sampling distribution, right? That's the bell curve that comes if you were to take every single possible sample that you could ever possibly take. Now, statisticians tell us that the bell curve, the sampling distribution, is centered on the true population value, but I have no idea what that is. If I knew what that was, I wouldn't be doing statistics in the first place. I would just go with that knowledge. So I don't know where that sampling distribution really should be, but I'm going to begin from a position of skepticism, and I'm going to assume that it's centered on 0. Now, why would I assume that, and why is that skepticism? So if we have a positive value for our slope, it suggests that as our x value goes up, our y value is going up. It's something like this, and there's a relationship between x and y. If we have a negative slope, right, as we increase on x, the prediction goes down, the y value goes down, and so there's a negative relationship there, but they're still linked. If our slope is 0, it means that there's no relationship whatsoever between x and y. It doesn't matter what's happening to x, it just stays flat. There's no change in y whatsoever. So a 0 slope means that there's essentially no relationship connecting these two variables together. So if I assume that the sampling distribution is actually centered on 0, I don't know this, I'm just going to make this assumption. What I'm essentially saying is I'm just going to assume there's no relationship out there. And I want to see if my sample and my results can square with that, if that makes sense, or if maybe that's a bad assumption. And so the way that I do that is, well, I actually don't do that. I allow SPSS to crunch the numbers and give me some math to do that. The way that we do that is we take our slope value, and so in this case, we'll talk about the GPA row, that slope that goes with GPA, the 5.041. We've got to figure out how that would fit on our sampling distribution. And so there's some math that goes into this, but essentially we convert that slope into what's called a t-statistic, which tells us where our sample falls on the sampling distribution that's centered on 0. And so in this case, our t-statistic is 3.2. And what that means is that I can count 3.2 standard deviations, or I guess they're called standard errors in the sampling distribution. 3 standard deviations up from the center of that normal curve, from that 0 point. 3 standard deviations up, and then a little bit more, 3.249. And that's where my sample falls. So it's not right there in the center. It's not right next to 0. It's out maybe in that right-hand tail. And that might give me a sense that that's a little bit of an unusual kind of result, that there's not a lot of samples that fall that far away from the center of the sampling distribution, but it certainly is possible, and that's where my sample falls. And so then I have to ask the question, okay, so I've placed my sample on the sampling distribution. What does that actually mean? And so let me walk you through this idea of the threshold of weirdness. I think a useful way of thinking about this is to refer back to a Chiefs-Rams game in November 2018, in which the two teams scored collectively over 100 points. I think it was 54-51 was the final score. Now, when I watched the game, I thought, wow, that's a really high-scoring game. But it wasn't until I saw this distribution of the point totals for every NFL game played from 1970 through 2018 that I realized just how crazy that Chiefs-Rams game actually was, right? So NFL games seem to follow kind of a normal distribution in terms of how many points teams score. It seems like on average, teams score a little over 40 points, and so roughly 20 apiece. Sometimes you get low-scoring games, sometimes you get high-scoring games, but you almost never get a high-scoring game like that Chiefs-Rams game. That was crazy. And so we can look in that situation and say that's something that happened once in 50 years. That was a really unusual event. Wow, that was amazing. But that sort of opens the door for asking the question, like, how do we know when something's amazing? How do we know when something's really unusual and really bizarre? And so I would maybe walk you through this idea of the threshold of weirdness, right? Where if I flip a coin in the air and I call heads and it lands heads, most people are not impressed. 50-50 shot. Half the time it happens, you call the coin correctly. Nobody's impressed by that. If I have a deck of cards and I say I'm going to draw a heart, and I draw a heart, nobody is impressed by that. They do the math mentally. They say that's a 1 in 4 chance. Yeah, it's not like you're guaranteed, but that sort of a thing happens all the time. I'm not that impressed. If I have a deck of cards and I say I'm going to draw the 2 of clubs, and I draw the 2 of clubs, that strikes people as weird. They start saying, hey, what's the magic trick? How did you do that? What's going on? That wouldn't have just happened. And so something happens between a 1 in 4 chance and a 1 in 52 chance where we cross over from, no big deal, that could just be random luck, to something weird just happened. Something unusual is going on here. And so statisticians have kind of narrowed that down. So that point, that crossover point, that threshold of weirdness is 0.05, or a 1 in 20 chance. That if it's a number higher than 1 in 20, so maybe a 0.1 or 0.2, 20% chance of something happening, people will shrug that off. But a 0.05, a 5% chance, a 1 in 20 chance, or more rare, people tend to sort of look at that and think, something is going on that doesn't seem to make sense. So using that idea that we can look at our sample, our sampling distribution, and look at where our sample falls and ask the question, how likely would that be to happen just by chance? That can help us get at this question about whether or not we should hold on to that skeptical assumption that we started with, or whether we should maybe believe our results. And so the way that this works in practice is that we calculate the area under the curve to the right of our sample in this case, or if we were on the other side, we'd go to the left, right? We're looking for how likely is it to get results that are more extreme than this? And we want to know what percentage of samples fall in that area. You can do this with calculus, but I wouldn't recommend it. What I would recommend doing is just using the numbers that SPSS gives you. And in fact, SPSS provides that percent or probability, percent of the area of the entire normal distribution, or the probability of having a sample land in that area, in this SIG column. So this is how we determine statistical significance with this probability or this percentage of the area. And so SPSS gives it to us in this column. And so for that GPA variable with the 5.041 slope that has a t-value that puts it a little over 3 standard deviations on the sampling distribution away from that center, from that assumption of 0, that would only happen 0.003. So about 3 times in 1,000 is what I'm working that out to be. That's pretty rare. I wouldn't expect that to happen every day. And so that leaves me with essentially 2 choices. Either I can conclude from this that my sample was probably one of the freakishly rare scenarios where we would get a slope of about 5, right? The just really bizarre situation that would put a result out here in the tail like that. That's possible, but it's really, really unlikely. The other possibility is that maybe that skepticism that I started with, that said there's no relationship at all, and where I put the sampling distribution down and plunked it down on 0 and said that's probably what's going on, maybe that initial assumption was wrong. Maybe the sampling distribution and the true population value should be adjusted and moved somewhere else. And in fact, maybe it would make more sense to just go with the 5.041 as my expectation, rather than trying to hold on to this idea that there's no relationship and my sample was just the 3 in 1,000 event that just seems so unlikely. So this idea of hypothesis testing, or evaluating the null hypothesis, or evaluating statistical significance, is really just getting down to, can I believe the results that I'm seeing? Is this likely to just be random sampling variation, or are the results so unusual that I have to conclude this can't be sampling variation? It's got to be that there's a pattern and a relationship connecting these 2 variables together. That's essentially what we're doing. Okay, now if you have that, right, that the R-square helps us to evaluate the overall effectiveness of a model, that we can look at the slopes and get a sense of like what's happening in terms of the relationships, positive and negative, and how that's changing my outcome. And this idea that if we look at that SIG column and those p-values, that will tell us how likely this result would be to happen by chance, and whether or not we should be skeptical of it, or whether or not we can accept that maybe something interesting is happening here. If you've got those 3 sort of things down, then when you look at the results of a regression analysis, you should be able to sort of put all these pieces together. And so this is a regression analysis by Lin and O'Neill from 1993, in which they analyze the effect on presidential approval, so the change in presidential approval, what they call rally, that occurs around international crises. And so the idea is there a rally around the flag effect, where leaders become more popular when there's an international crisis? And so there's a bunch of different variables. And over on the left-hand side, I kind of talk through how each of those variables are coded. And if I look at just that first New York Times variable, there's 3 pieces of information that are being provided. There's the B, the slope, that coefficient that we would pull out of those SPSS results. That's telling us what the relationship is between our X variable and our Y variable. There's the standard error, which if you were looking carefully at those tables, there's a standard error column there. We can use that to calculate our T statistic and figure out our P statistic. I wouldn't worry about standard errors and studying them too hard. Instead, I would just shift down to that third piece of information, the p-value, and that tells you whether or not this relationship is likely to occur by chance. And so we can kind of look at that New York Times variable and look at how it's coded. And so it's 2 is the code that gets used when there was a crisis that was a New York Times headline. 1 is a crisis that made a front page story. And 0 is a crisis that was not covered on the front page of the New York Times. So this is getting at sort of how big of a deal in terms of media coverage and public attention was this particular crisis. And I would imagine the crises that get more attention are more likely to get, have an effect on presidential approval. And in fact, if you have, no coverage on the front page, the models suggest that if you plug a 0 in that equation and multiply your slope 0.98 times 0, the effect would be 0. It would cancel itself out. If you had a front page story, however, instead of putting in a 0 into your equation, you'd put a 1 in there, multiply that by your slope, and the result of 1 times 0.98 would be 0.98. And so we could say, well, hey, if the story gets covered on the front page of the New York Times, even if it's not a headline that's there, that's going to have the effect of increasing the president's public opinion approval rating by 0.98, basically a point. And if it's a headline, oh my gosh, instead of putting a 1 in there, we're going to put a 2 in there. And so it's increasing it by 0.98 times 2, which is 1.86 maybe. So not quite 2 percentage points. That would be the increase or the bump up that we would get in terms of presidential approval from having a crisis make the front page headline for the New York Times. Okay, so maybe that's interesting. We might look at that and say, okay, well, news coverage might be related to presidential approval. I can see that. But as you shift down and look at that p-value, the p-value is 0.1. So essentially a 10% chance of this happening if the null hypothesis, if there's no relationship, if we're assuming that skeptical zero-centered sampling distribution. Essentially, there's a 1 in 10 chance that this would happen if there was no relationship whatsoever. And that might not meet our threshold of weirdness. So even though we see a pattern and a relationship and a slope, and it maybe makes sense, the results aren't really strong enough that we can say, this is something real. In fact, you might look at that and say, it looks like it could just be happening by random variation and just by chance. If we shift down and look at that ordSever variable, which is ordinal severity, it's a measure of like how much a crisis threatens the core national security interests of a country. So 10 is like the survival of the country is in danger, and 1 is there's an air base in some other country that gets used for, I don't know, landing planes for not important reasons, and that air base might go away. So something that's not like central to a country's survival. That relationship seems to be fairly important in terms of every time you increase your ordinal severity by 1 unit in that march from 1 to 10, you increase presidential approval by 1.45%. And so that seems like it's having a pretty big effect. And in fact, if we look at the p-value, the probability of that kind of a relationship happening by chance, if we're assuming sort of skepticism, is 0.01, so 1 in 100. And that seems like something that wouldn't just happen by chance. And so we might conclude in this situation that we shouldn't pay too much attention to the relationship that's going on between the New York Times and presidential approval. But this severity, the intensity of that crisis and how much it threatens national security, that does seem to be related. And there seems to be a connection there between that and presidential approval. And so we could maybe focus our attention in on those sorts of things that have those p-values that are really small. Now, it's increasingly becoming the case that when regression results get reported, rather than reporting the p-value, people will just put asterisks in place. And so you might see 1 or 2 or 3 asterisks set next to those slopes. And that's just saying, hey, these results are so unusual that we can't hold on to that skeptical assumption. These results seem like they're something that wouldn't happen by chance. These results seem real. And so it actually makes it a little bit easier to pick out what are the factors that are really driving that outcome, because you just sort of scan through these tables and look for the slopes and the relationships that have asterisks attached to them. Okay, so we can look at those various different numbers, and we can figure out, what's the direction of the relationship, positive or negative. We can figure out maybe how a change in our x variable is affecting our y variable. We can assess whether or not it's statistically significant, whether it's likely to happen by chance, or whether it's something meaningful that would be unlikely to just result from chance. And then lastly, we can scan down to the bottom, and we can look at, in this case, the adjusted R-square, which is similar to the R-square, and that tells us how good of a job our model is doing explaining presidential approval change, right? And so in this case, we have an adjusted R-square of about 0.21. So we're explaining 21% of the variation in the change of presidential approval ratings around these international crises. So we're capturing something. We're able to account for some part of that variation, about a fifth, but that means that there's still a lot that we're not fully accounting for, not fully explaining. And so that would then be another thing that you could look at with these models. It would help you get a sense of what's happening and how they're operating.